In this lecture, we will discuss how do you evaluate or which criteria do you evaluate different instrumental methods. I think we already know well there are so many analytical methods out there. And most of the analytical methods out there, they perform fairly similar functions. I'll give you an example. If you take AAS, atomic absorption spectrometer, most of which you guys have done in the class, and you compare it probably with the ICP, which you're gonna do this week, inductively coupled plasma. Now, both of them, are atomic, spectrometric, types of techniques. And so essentially, they analyze different types of elements. So how do you then determine which is the best instrument to use for a certain application? Well, they perform essentially the same purpose. They are used for atomic spectroscopy. And so today we're gonna discuss, different types of indicators that you can use to evaluate different types of instrumental methods and to perform, comparative studies, or evaluations between the methods. And this is what we refer to as the figures of merit. And I'm sure you guys have heard me talk about them. And those of you who did Chem 211, you already know about them. So the six important and often quantitative, figures of merit, includes, precision, accuracy, sensitivity, selectivity, quantification limit, limit of detection, limit of linearity, and dynamic range. And in fact, you're gonna see that they are part of, the calibration plots, so you can actually determine them, from calibration plot. So in this chapter, or rather in this lecture, I'd like you guys to know how to actually determine them quantitatively as well as be able to explain what they are in a qualitative sense. Now, of course, there are other types of, ways of evaluating instrumental methods that are not in this category of the figures of merit. And some of these include, the speed, how quickly, can you use the instrument, sample throughput, how many samples can it run possibly in an hour. Does it need a lot of operator skill, or can somebody out there, the public, actually without a lot of expertise use it? And that's a good thing. And of course, the cost of the instrument and so on. So these are other considerations, obviously, that you can use when you're choosing an analytical method. But the focus, for my lecture today would be on the 6 key figures of merit that you should always pay close attention to. First, precision. Precision really refers to a measurement of random or indeterminate error, that is present in your instrument. First things first, all instruments out there have got some aspects of indeterminate or random error. And so if you analyze a sample, 10 times, you essentially would not, a sample, exactly the same sample, you analyze it 10 times, you won't get, the same measurement. Essentially you would get some randomness, in the number that you get. And that is what you refer to as, precision. For example, if you look at, the figure shown here, you can have a data set that looks like this, that is very closely distributed in one area, whereas you can have a data set, that looks like this, that is fairly distributed in a wider area. So you can see, that this data, is more precise, meaning if at all you had, a mean value plus minus the standard deviation here is fairly small, compared to the standard deviation, in this case. So I should say actually precision or precise data doesn't necessarily mean that it is actually accurate. As you can see, this data can be very, very precise, but it can be very, very inaccurate, meaning, of course, it's very far, figuratively, from the bullseye. Whereas these other case, the standard deviation is very large, meaning precision, is very poor, but actually the data could be more accurate, so don't confuse the two. Precision and accuracy are fairly different. Precision only tries to indicate, how closely the data is distributed, around the mean. So if at all the mean is there, was a distribution of the data around the mean. And so you measure it using, standard deviation. And of course, there are different types of standard deviations out there. There's the absolute standard deviation that is symbolized, by S. But also, there is variance, which is symbolized, by the square root, of the absolute standard deviation. But there's also what you refer to as, the standard deviation of the mean, which is, the absolute standard deviation divided by the root of the number of measurements. And that is what you refer to as, the standard deviation of the mean. But there's also what you refer to as, the relative standard deviation. And of course, this is a repetition of what you know. The relative standard deviation, would be the absolute standard deviation, divided, by the x bar, which is the mean, times 100, and then it becomes, percent. I hope it's fairly clear. And that's what you refer to as relative standard deviation. So as you're reading papers, you're going to see some people defining precision using all those different methods, of standard deviation, absolute, standard error of the mean, and variance, and so on. So when you hear people talk about repeatability, really they are referring to the standard deviation, really, that is acquired by the analyst using the same instrument, on the same day. Okay, and so that's a measure, of precision. But a more robust measure of precision, is where you use the method and you analyze the sample, over different days, using various instruments, of a long time. And that is what you refer to as reproducibility, of that method. So, for example, for some of you making census, to assess, how reproducible, it is, you possibly need to make 3 different types of census, and then you analyze, your sample on those census on different days, and that is what you refer to as robustness or reproducibility, which is still a measure of precision. And I hope that's clear, the difference between repeatability, and reproducibility, which are aspects, of precision. Accuracy, on the other hand, refers to as how close, your data is to the true value. And that's what I use to grade, your experiments. I know the true value of the unknowns that I give you, and you generate a calibration, and then you determine the concentration of the unknown. And what I do is to determine, how far your data is from the true value. And that is what you refer to as, the bias, how accurate, your data is. Now, it's very important, to know that accuracy, can be affected, by different aspects. One, is the instrument. The instrument itself could be fairly inaccurate, possibly, due to these reasons. Maybe the signal is dying out, and so on. Maybe there's drift in the instrument, over many days. Maybe it's being affected, by temperature effects. Maybe it's not very well calibrated, it's a big problem. Instruments need to be very often calibrated. And if at all they are not calibrated, the accuracy, of the output, is affected. But other than the instrument, accuracy could also be affected, of course, by the analyst. And hopefully, the analyst, meaning you become fairly skilled, such that, you do not make, errors in your measurements, that affect, the accuracy. But other things that can affect accuracy is the way you work up, your sample. For example, sample preparation, it may have matrices, and those ones may equally, of course, affect, the accuracy of your analysis. There could be other things happening during sample preparation, like isomerization, dimerization, chemical reactions, that are taking place that are not accounted for, could affect, accuracy as well. And as we've done before, you realize the solution, of course, to this, of course, is standard addition. Remember what we said, standard addition calibration, is a solution, to matrix effects. Another solution, of course, is if you had a method blank, it can account, for some of these things, slow reactions and so on, can be accounted for, by the method blank, or ideally an ideal blank, which we said last time that it's not very practical. Now, the other figure of merit, is sensitivity. And sensitivity really refers to as ability of the instrument to differentiate between two small changes in the analyte concentration. Now, there are two types of, sensitivity. There's what you refer to as calibration sensitivity. And calibration sensitivity, you just, get it, from the slope, of your calibration, okay? So it does not really account for data distribution. On the other hand, you've got analytical sensitivity, which just means, the calibration sensitivity, which is M, divided by the standard deviation, of the measurements. So you can see in this case, if you put in the error bars in your calibration, like in this case, you can see, that it's accounted for, in the analytical sensitivity. And so you can see actually sensitivity, is affected not only by the slope of the calibration curve, but it's also affected, by the reproducibility or the precision of the instrument. Because like you can see, if I put in the error bars in that case, all that, becomes, the analytical sensitivity. And so, which is a much more robust way of defining sensitivity compared to calibration sensitivity. All right. So sensitivity is affected by the slope as well as, reproducibility or precision, of the instrument. Another measure, figure of merit, is what you refer to as the limit of detection, or the LOD, which refers to how low can I go in terms of determining the concentration of the analyte, in terms of, how low can the instrument actually detect. So essentially, the limit of detection is trying to answer the question, is the analyte present or not, and can the instrument tell me if the analyte is present, or not. Now, so the limit of detection really is dependent, on the signal to noise. And the next, lecture, I'm gonna talk a lot about the noise, because we are saying, that the limit of detection is very, very close, to the noise level. So the signal is very, very small, meaning it's the minimum signal that I can associate, with the analyte. All right, so maybe another nice definition is a minimum signal that the instrument can give me that I can associate, to the analyte. Now, there's what you also refer to as a limit of quantification. And the limit of quantification is very similar to the limit of detection. Now, the only difference is it defines the minimum, peak, that I can get, but I'm fairly confident, that it is reproducible. All right. So it's a minimum concentration, that is obtainable by a certain method within a certain level of confidence limit, meaning it's fairly reproducible. And so I can be fairly confident, about the presence, of that analyte, using the determined concentration, meaning the data is fairly accurate. So take note of that difference. The limit of detection, so the data that I get may be the concentration of the sample. The standard deviation would be very, very high, for the limit of detection for me to be very certain in terms of quantifying it. On the other hand, the limit of quantification is where you've got the standard deviation is small enough, and so I'm fairly confident, that my analyte can be quantified reliably. It can be quantified reliably. All right. So if you get, data, you get a signal, and the signal, is equals to, the standard deviation of the blank plus 3 times standard deviation of the blank. That's what you refer to as the limit of detection in signal units. So the limit of detection in signal unit is equals to, or is calculated as standard deviation of the blank plus k, but the k in that case is equals to 3 multiplied by the standard deviation of the blank. The limit of quantification, on the other hand, is calculated exactly the same way. The only difference is instead of 3, you substitute it with 10 for the k, and that would be the standard, and that would be the limit of quantification. Remember, in signal units, you can see signal, signal, signal. So the unit would be signal units. However, in most cases, we are interested, with the limit of detection or the limit of quantification in concentration units. So how do you determine the limit of quantification or the LOD in concentration units? The only thing that you do is you take the signal limit of detection or limit of quantification, and all what you need to do it is divided by the calibration sensitivity, and that's what I have here, divided by the slope. And essentially whatever you get, is gonna be equals to, concentration units, say ppm, if at all those are the units, in your x-axis. So if I ask you to determine the concentration limit of detection, make sure, you divide, the signal limit of detection divided by the slope. And it's the same with the LOQ. The signal LOQ, divided by the slope gives you the concentration limit of detection. The other important figure of merit, is the limit of linearity, and it's fairly straightforward. It refers, to the largest concentration at which, the instrument response deviates from linearity. So the point at which the instrument response is no longer linear relative to the concentration is what you refer to as the limit, of linearity. Now, dynamic range, on the other hand, a very important figure of merit, refers to the range of concentration, that the instrument is responding linearly, so the region of the calibration where the instrument response is linear is what you refer to as a dynamic range. And so dynamic range is calculated often as limit of linearity divided by limit of quantification. Take note of that. It's divided by limit of linearity divided by L or Q is what you refer to as dynamic range. Of course, the biggest, the better. It means that you've got a very, very wide range, which can give you a good linear response. And so, you can determine the concentration of the unknown. Ideally, you want 5 to 6 orders of magnitude for dynamic range for a very robust, good instrument. So the other type of figure of merit is what you refer to as selectivity, and this is very, very important, when you're doing your census work, and some of you are doing that for your projects. Selectivity, refers to the ability of the instrument to only respond to the analyte while it's being blind, to the matrices. It's not being interfered, by the matrices. And so essentially, you want your sensors, for example, to be completely blind to the matrices, but very selective, to the analyte of interest. And so you calculate, selectivity using what you refer to as selectivity coefficient, which would be the response, of the matrix divided by the response or the sensitivity, in this case, of the analyte. And the smaller the K is, the better, the more selective, your analyte is, or rather your method is, towards your analyte. So take note of that. You just take the response to the matrix or to the contaminant divided by the response, to the analyte, and that gives you the selectivity coefficient. And as I said, you want the selectivity coefficient to be very, very small for your sensors, to be very good. So that's all that I'm going to say, about figures of merit. Now, remember the importance again of figures of merit is really to help you make decisions on which instrument do you use for a certain problem. And so in this course, it's very important, to remember how to apply the figures of merit, to compare different types of methods. And, you may likely, come across that kind of questions in the exams. But in the industry, it's a very important, thing to understand the figures of merit, of different types of instruments, because they help you make a decision or recommend, which is the best instrument to use for a certain type of a problem. Now, in the next lecture, we're going to talk about noise. You remember all what we've been talking about, is instrument response. An instrument response comprises the signal, which is what you are interested in. But unfortunately, as we said, every instrument has got a noise in it, and noise accounts for, the random errors. The random errors, is what is accounted for by noise. And so in the next, lecture, we're going to talk about, the instrument response in terms of optimizing the signal, whereas reducing the noise, and even the ability to quantify the noise, relative to the signal is what we're going to talk about in the next lecture.